Today, we're going to calculate some volumes, and we're going to use multiplication because that's all volume is. Volume is area of the cross-section multiplied by the height. Now, since this is single variable calculus, we only get to use our delta variable has to be in that height department. So that's where our delta variable is going to be. What we're going to do is we're going to make a stack of books that are getting infinitely thin. So here we have a hemispherical bowl with a radius of 8 centimeters, and the bowl contains water to a depth of 5 centimeters. And we want to calculate how much water is in the bowl. The important thing to realize is that the water is not in the shape of a hemisphere of radius 5. It's a piece of a hemisphere of radius 8, but it is not a hemisphere of radius 5. So if I think of the middle, I guess, of the water up here, it is not 5, it's 5 units from the surface down to the bottom of the bowl. It is not 5 units from the surface to any other point on the bowl, because we're not sitting in a circle of radius 5. We're sitting in a circle of radius 8. That's the main thing that I want to point out. That we don't have a circle of radius 5 sitting inside a circle of radius 8. All right. So here's what we're going to do. We're going to look at the water as a stack of books that are infinitely thin. So that means we're going to slice horizontally. So our water is going to be a bunch of slices. Now, when I draw that slice in the area problems are always rectangles. But when I draw that slice, I have to think this is a slice from a hemisphere. So the height is going to be my delta variable. My height is going to be the delta variable. But when we look at this from when we look at this from the side, we see this rectangle for the slice. But if we look at this from the top, the cross section is a circle. So this is a hemisphere. So the cross section is a circle. So since the cross section is a circle, the area of the cross section will be pi r squared. So the volume of the slice is pi r squared times the height. Now, since this is the side of a circle from the side, we can label the radius. There's the radius of that circle. What we need to do is relate the radius to some x variable that needs to be a vertical variable. So I've identified what the shape of the slice is. It's a circle, pi r squared times h. I've identified my delta variable, which is going to be the h. So that's going to be my delta x. Now I have to define what I mean by x. There are two reasonable places to put the x. I'm going to put it in the place that we put it last time. We had a circular cross section. And I'm going to say it's going to go from the top of the bowl down to the slice. This is not the only place we should put it. We have 3 reasonable choices of where we could put the X for this problem. Once I decide where X is going to go, we have decided where X is equal to 0. One end is the slice, the other end is 0. So that means 0 is at the top of the bowl. Furthermore, down is the positive direction. So X is the distance of the slice from the top of the bowl. And that means down here at the bottom, X is equal to 8, as the radius of the bowl is 8 centimeters. Another thing that we want to note here is that eventually we're going to be integrating where the slices of water are. The slices of water don't start at 0. There's no water at the top of the bowl. The radius of the bowl is 8 centimeters. The depth of the water is 5 centimeters. So the water doesn't start until 3 centimeters. Eventually, we're going to integrate where there are slices of water, where the slices of water are, and that starts at 3 and goes up to 8. Any questions? Now I just need to get a relationship between that radius of that slice and this value X. And to do that, we're going to do the same thing we did before. We're going to make a right triangle from the center of the bowl, not the water. I've got to have a constant hypotenuse. And I only get a constant hypotenuse if I measure from the top of the center of the bowl. Once again, this triangle has to go from the center of the bowl because that's the only way we're going to get a constant hypotenuse. But now we have a relationship between X and R. X squared plus R squared is equal to 8 squared. So R is the square root of 64 minus X squared. So now I can plug some stuff into the volume of my slice. The volume of the slice is pi times the radius, which is the square root of 64 minus X squared. Squared times the height, which is the delta X. Questions on the setup? This setup is the key. We are done with the problem now. The rest is just details. We're going to do the rest of the problem by hand by grabbing our calculator and punching the definite integral in. So once we have the slice set up, we're done with most of the setup of the problem. The very last thing would be decide where we're going to integrate. Also, clean this up. It looks terrible. This is a big mess. It needs to be simplified. I'm going to factor a pi out of the integral. And the square root of 64 minus x squared is just 64 minus x squared. My discrete delta x becomes a continuous dx. And we integrate where we have a slice of water. The water doesn't start until 3 centimeters down from the top of the bowl. So we integrate from 3 to 8. 0 to 5 would be the top 5 centimeters of the bowl. But that's not where the empty space is. But that means that the empty space would be on the bottom. We don't have 3 centimeters of empty space on the bottom of the bowl. We have 3 centimeters of empty space on the top of the bowl. So the 3 down here, because the water doesn't start until 3 centimeters from the top of the bowl. Water starts at 3 centimeters from the top of the bowl. So it looks like we have 497.42 cubic centimeters of water. I didn't state it at the beginning of this problem because it's too much to write. It's not too much to write, but I don't want to write it. I am usually going to ask for 5 significant figures. Once I ask for 5 significant figures, that means that any integration should be done on a calculating machine. You can do it by hand if you want to practice, but if I say round your answer to 5 significant figures, the calculator is where you're going to get your 5 significant figures. If you want to make it look like you did the problem just by thinking about it, do this without the pi. Get rid of the pi. Oops. Dang it. I have to type the whole thing in again. So here we get 158 and a third. And so you can say it's like 158 and a third times pi, because I did it by hand. We can see where the third is going to come from. Because we're integrating an x squared, that's going to produce a 1/3 x cubed that we're plugging integers into. One of them is going to be able to cancel out, but the other one is not. Because the 3 has a 3 in it, but the 8 doesn't have any 3s in it. So we're going to have a 1/3. Or you can be like 475 over 475 pi over 3. Then you could really give off that air of, I am a mathematician, and 475 pi over 3, that makes perfect sense. But if you're going to be an engineer about things, then it's 497.42. That's 5 significant figures, as specified by the client. Any questions? If you're unfamiliar with 5 significant figures, you start on the left and you write 5 digits. There's other things that go into it. Like if we have a times 10 to the, then the times 10 to the part doesn't count. So five significant figures in scientific notation. Since this is hundreds, we could also write this as 4.9742 times 10 squared, because it's hundreds. And that would still be five significant figures, but in scientific notation. The times 10 squared is not adding any digits. It's just telling us where this 4.97 is. It's not that strange. We do this all the time. How much did you pay for that car? 20,000. We don't say 20,000. We just say 20 times 10 to the third. Any questions? Is everybody okay? So let's adjust things a little bit. Let's suppose that instead of a hemispherical bowl, we have a bowl in the shape of a half of a cylinder. What's a half a cylinder called? A hemicylinder? Or is it a semi-cylinder? Or am I making up words and it's just half a cylinder? It seems like something I should know, but I just don't. So in the hemisphere, now apparently I'm going with hemicylinder because I'm gonna call hemisphere, but maybe I'm just a Mopar guy, I don't know. The hemisphere, our cross section was a circle. If we look at this bowl from the side, one slice is going to be in the shape of a circle. In our hemisphere, so what we're going to switch to now is we're going to think of a half of a cylinder. Oh, I don't know why it's so flat. Our half a cylinder is going to use the same picture from our hemispherical bowl. We're going to have a slice that looks like just a line, but in a half of a cylinder, that slice is going to be a rectangular solid. So where our hemisphere had a cross-sectional area of pi r squared, our rectangle has a cross-sectional area of length times width. Moreover, in this half cylinder situation, the length is constant. What isn't going to be constant is the width. Down at the bottom, the width is equal to 0. And then as we go up the cylinder, we'll get the width will increase to the diameter of the cylinder. So let's draw this picture and then track the changes. See how things are different. So this is still 5. Depth of the water. Bowl is still 8. I'm still going to draw a horizontal slice of water. I'm going to use a different variable to differentiate it from, no, I'm going to use the same variable. I'm not switching that up yet. Delta X is going to be our height. I'm going to still use the same X, which will be the distance from the top of the bowl to the slice. So the top of the bowl is still X equals 0. Surface of the water is still at X equals 3. Bottom of the bowl is still at X equals 8. So if instead of having this hemispherical bowl, we have a half of a cylinder with a radius of 8 centimeters, and let's say a length of 11 centimeters. Oh, all of a sudden, pretty significant figures. I'm going to use 5 for my answer anyway, so I don't know why I'm worried. So in this situation, since we don't have a hemisphere, we're not looking at that slice as a cylinder from the side, because the slice is not a circle. This slice is a rectangle from the side. So the volume of the slice is length times width times height. Our length is fixed at 11. Our width, we're going to need an expression for. And our height is going to be the delta X. I forgot to label the width. Right. So when we're looking at this from the side, we can't see the length. The length is coming out of the page. Oh, no, that'll be right in the way. The length is going into the page 11 centimeters. That's the part that we don't see. We're not looking at it from this angle. We don't see this length because I'm going to orient this so I could see the half circle in the front. But notice that the width is just 2 of the radius that we had before. So for the width, I could do the same thing we did up here. I could use a triangle, a right triangle from the center of the bowl down to the slice, where one leg is going to be x, the other leg will be half of the width, and the hypotenuse is still 8. But there are 2 copies of the quantity we had before, 64 minus x squared. And then the height is still delta x. So notice that the width is just 2 of the radius that I had from the previous problem. Any questions? Yes. Yes. So I'm using the same triangle I had in the previous problem. And in the previous problem, halfway, since I was looking at the radius, I was going from the middle to the bowl. And so that's half of what I want now. The radius is down here. The radius from before would have been right here. That radius is half of the width. So that's why I want to use 2 of them. We can also look at that if we look at that triangle. The triangle is only covering half of the width. So I've got x squared plus 1/2 the width squared is equal to 8 squared. So W, we still got this 1/2 after we solve for the base. And so W will be 2 square roots of 64 minus x squared. Now we just need to add up all the values into a definite integral. And so our total volume see. I have the 11 and the 2. I'm going to pull both of those out and have just 22 times the integral of 64, the square root of 64 minus x squared. Notice that the square root is not getting squared out here. My discrete delta x becomes a continuous dx. And we still only integrate where there's water, from 3 to 8. And that's still just going to be a calculator problem. So 590.49. We divide out the pi. We try to convert this to a fraction. It's not going to give us a fraction, so we'll just leave it as a decimal. If I want the exact fraction, if it is an exact fraction of multiple of pi, then I would have to integrate this by hand, but we don't have that technique yet. This would require trigonometric substitution. So we only know half of the substitution story. We don't know the trigonometric substitution part. But that's okay. We got machines to calculate our definite integrals. Any questions? Notice that the base of both of these problems was that volume is an area of the cross section multiplied by the height. We just had to take a picture of what we're looking at and figure out what the cross section is. What is the shape of the books that are making this stack of infinitely thin books? Here's how I'm going to go through and score one of these problems. If you happen to write one of these problems for me on a homework, a quiz, or a test, actually just plug in the number for the homework. Canvas handles that. But if I ask you to do one of these problems and show your calculations, here are the calculations that I look for. The first thing I look at is your answer. Do you have the correct value to 5 significant figures? If you do, that makes me give the rest of it a cursory glance. I still look at it, and the least important part of this whole problem is the answer from your perspective. From my perspective, getting 5 significant figures, probably not going to happen by chance. So I can kind of go through the rest of it quickly. I go back and I see the endpoint, where you're integrating from 3 to 8. I consider this to be an important part of setting up a definite integral. What values are you going to be plugging into the function? So that's the next thing I look at. Integrating from 3 to 8. And the function should look like I expect it to look. Then I will take one step back and I will check out where you're developing the volume of the slice. And I can see a length times a width times a height. And then I will look at how you labeled things. With X labeled this way, integrating from 3 to 8 is the correct answer. Any questions? What I'd be looking for here is a mismatch. So if you set up your X from the top of the bowl to the slice, and you integrated from 0 to 5 and had the correct answer, that means you switched methods halfway through. And so your answer is going to be inconsistent. Your integral is going to be inconsistent with how you labeled things. So let's talk about those labels. Let's go back to our hemisphere, but label things differently. If you recall, I said that there are a few places that we could put the X that's reasonable. So this is still 8. I'm going to put some more water in the bowl. And it's still 5. We're going to make a slice down here. The volume of the slice, since it's a hemisphere and the cross section is a circle, the volume of the slice will still be pi r squared times h. In these volume is area times height problems, height is your delta variable. So my stack of books is getting infinitely thin, so this is my delta variable. I'm going to call it delta y, but that's going to be my height. But I'm going to define y in a different place then we define x. X was the distance from the top of the bowl down to the slice. I'm going to measure y as the distance of the slice from the bottom of the bowl, which means I made my slice way too low. That's all right. I'm going to say y is the distance from the bottom of the bowl to the slice. Once we make that choice, we have decided that y equals 0 down here at the bottom of the bowl. The water ends at y equals 5, and the top of the bowl is at y equals 8. So thinking ahead to where we make the build the integral only represents slices where there's water. Here, the water starts at 0 and ends at 5. We're looking at a circle. As from the side, we're looking at a circle, and we need to relate the horizontal stuff with some vertical stuff. And that means we're going to use a right triangle. The right triangle always has to be in the same place. It's not a technique, it's a trick. It's just a trick for relating horizontal to the vertical when we're looking at a circle from the side. That still needs to go from the bowl, the center of the bowl, down to the slice, so that the hypotenuse is always the radius. That gives us a nice constant hypotenuse and a way to relate the radius of the bowl, or sorry, the radius of the slice, and the value y. But notice that y is down there underneath the slice. I need to know what y is, or how this leg of the triangle relates to y. So if this whole distance is 8 and this bottom piece is y, then this leg of the triangle is 8 minus y. And now I can say 8 minus y squared plus r squared is equal to our 8 squared. So our radius will be the square root of 64 minus 8 minus y squared. Questions? I realize that we could simplify this, but why are we going to do algebra? I've got an expression for the radius. It's a little bit clunky, but why do algebra in the middle of our calculus problem? The more things that we try to do, the more likely we're going to mess something up. So let's just leave it. Now we're ready to put all of our information into the volume of the slice. The slice is pi times the radius, and the radius is now this, it's a little bit messy, square root 64 minus 8 minus y squared. But the radius gets squared, and then we multiply the cross-sectional area by the height, which is delta y. So we've got the setup for our integral. So r of a total, I'm going to factor out the pi. It's going to be the integral of the square root, and the square will cancel out. So I'll have 64 minus 8 minus y squared. My discrete delta y becomes a nice continuous dy. And now the other big difference. Now, instead of integrating from 3 to 8, since y is measured from the bottom of the bowl, we're going to integrate from 0 to 5. From 3 to 8 and from 0 to 5, still 5 centimeters of depth of water. And we get the same 497.42. Any questions? Here's what you want to do. For the next three integrals after you review these. So when you review these, the next thing you would want to do is do the half cylinder. Calculate the half cylinder, but with this y, define with y instead of x, use the same y. And then do both with a different value of the variable, or a different variable. And then do both define a new variable z. So your height is going to be a dz, and let z be the distance from the surface of the water to the slice. So just define z to be the surface of the water to the slice. Remember that the triangle, where you get the relationship between the horizontal and vertical, still has to go from the bowl. So we can't just move the triangle down here because we won't have a constant radius. It's got to be from the bowl where we have the center of the bowl, where we have a constant radius of 8. Any questions? So those are the 3 problems that I would like you to work on after you review these. Any questions? Comments? All right. There is no class on tomorrow. There is no class on Monday. So I'll see y'all on Tuesday. Everybody have a nice 4-day weekend. And we'll just start at the beginning because you'll all forget it by the time we get that far. All right, that's it for this week. I'll see y'all on Tuesday. Everybody have a good weekend. And thanks for playing.